Okay, welcome to Power System Analysis. I'm Dr. Tay, your course instructor for this subject, and I will be taking over from this chapter onwards. Okay, so let's begin. We begin by looking into this simple 4-bus network in which we will use it to derive its power flow equations, and which we can later on use them to form a generic power flow equation. So notice that the circle over here represents generator. The branch here, they are the transmission lines. And notice also the impedance value given to you on the branches. And these two values represents the internal impedance of the generators. They are all given to you in only their imaginary form, lacking of their real part. This can be understood by analyzing how transmission lines and generators normally behaved in a real-life network. In practice, transmission lines transmit power over a very long distance and power losses are kept to a very low level. And if that happened, we can essentially say that the resistance on the line is very low, and we can consider them as zero in our analysis. And the same can be said for our generators as well. Generators are understandable, very efficient in injecting the power generated by them into the network. And if that is the reason, and if that is the case, then we can conclude that the resistance in the generators are actually very low as well, and we can ignore them or not consider them in our analysis. So that is the reason why impedance given to you are only in imaginary form. However, if in your exercise you notice that the values of the resistance are given to you, you should include them into your total impedance value. So in power system analysis, we want to convert our impedance into admittance by taking the inverse of the impedance. So impedance is given to us as Z. We take the inverse of Z and we get Y, which is our admittance. And notice just now I mentioned that Z is given to you only in the imaginary form, and sometimes you will be required to consider as well their real part, which is the resistance. This is how you are going to do it if the resistance value is given to you. We simply add on the term of the resistance without much trouble over here. So we go on and convert our 4-bus network into this format, which is when we convert our impedance value into admittance value. And the generators, they are all converted into current sources as I1 and I2, such as this. And then we can go on and analyze them. So this is the network that we had just now. To begin our analysis, we need to recall back our Kirchhoff current law, okay, which you all learned in your circuit analysis 1. So Kirchhoff current law says that the sum of all the current entering a particular node is the same as the sum of all the current exiting a particular node. So instead of having nodes in our power network now, we have buses, okay, given to us as bus 1, 2, 3, and 4. So if we apply KCL, okay, at bus 1, you notice that the current entering bus 1 is I1. And how about the current exiting bus 1? We are not given the information on that. And if we are not given information on that, we can assume the directions of the current flow away from bus 1 as this, and this. And when we look at bus 2, the current flowing into bus 2 is I2, and the current flowing away from bus 2 is not given as well. So we assume them as this, and this. And same as bus 3. The current flowing away from bus 3 is this, and there is no current flowing into it. So for current flowing away from bus 4 will be this. There's no current flowing into it. And by now you should notice that there is a contradiction in certain branches. For example, if you look at this branch, when we look at this branch and this bus, we say that the current is flowing from bus 1 to bus 2. But when we look at bus 2 and this branch, we say that the current is flowing from bus 2 to bus 1. So there is a contradiction in the definition of the current flow in certain branches. Well, it doesn't matter at this point because later on you will notice the calculations of the derivations of the equation itself, it will cancel off the contradictions, and we will be able to obtain a clean value of current later on. Yeah. So if you look at bus 1, the current that is flowing into bus 1 is given to us as I1, and that is equal to the current flowing away from bus 1. Away from bus 1 to 0, bus 1 to bus 2, bus 1 to bus 3. And that is given to us as the first equation. I1, okay, into bus 1 is equal to the current flowing away from bus 1. The first term is V1 multiply Y1, 0, which is this, which is on this branch. The current flowing on this branch is the difference between the potential on bus 1 and ground, which is 0, multiply with the admittance on this branch, Y1, 0. And the current on this branch will be the difference between bus 1 and bus 2, multiply the admittance Y1, 2. The current on this branch is the difference between the potential of bus 1 and bus 3, multiply the admittance Y1, 3. So now you notice, right? You notice the reason that we want to convert our impedance into admittance by taking the inverse of the impedance itself, so that we can avoid writing divisions on all these terms. And you should expect that if we extend this benefit to all the other equations, we avoid writing divisions on all our equations. And that actually makes our equation more manageable and less messy, especially when we decide to put these equations into our computer for solutions. Computers are better in handling multiplications than divisions. Yeah? So with the equations that we have obtained over here, we can go ahead and rearrange them in terms of their voltage term. So all the terms belonging to V1, we group them together, and so as all the terms of all the other voltages. So we group all the terms belong to V1, V2, V3, and V4 in each of the equations, and then we will get this one. So V4 is not written here, meaning that the terms are 0. V1 and V2 is not written in this equation, meaning that the terms for V1 and V2, they are 0. Now, before I proceed further, let's take another look at equation number 4. Yeah, equation number 4. So equation number 4 is derived based on there is no current injecting into bus 4, that's Y0 over here, and that is equal to the current exiting bus 4. Current exiting bus 4 is the difference between V4 and V3 multiply Y43. Yeah, Y43. And when we look at bus 3, in equation number 3, and the final term over here, we define that the current is flowing from bus 3 to bus 4. So if we define that way, then the current will be V3 minus V4 multiply Y34, given to us as this term. So I hope you notice that when we look at the same branch, but from a different bus, we actually get a different notation of the same admittance. Y34, versus y43 is one example. y12 and y21 is another example. y13 and y31 is another example. It doesn't matter actually how you write the emittance notation, whether it is y34 or y43, because they are actually referring to the same branch. So I hope this is this doesn't create confusion. Yeah? The reason we write y34 in this equation and not y43 is to be consistent with our derivations of the equation, because when we look at bus number 3, we want to be consistent, so we look at the emittance from the perspective of bus 3 when we are deriving equation number 3, so that all the terms, especially the emittance, start from bus 3 to other buses, and so as the same concept is applied onto other buses as well. Yeah. So with the equations that we had just now, okay, with the equation that we had just now, we now want to organize them into a more compact manner. And we actually notice something interesting over here. In each of the corresponding term of the equations, meaning the first term of first equation, the second term of the second equation, the third term of the third equation, and the fourth term of the fourth equation, they are unique to each of them. Okay, they are unique to their corresponding equation. Recall that y10 is the branch connecting from bus 1 to ground, y12 is the branch connecting bus 1 to bus 2, y13 is the branch connecting bus 1 to 3, which are all the branches connecting to bus 1. And if I take the third equation, for example, y31, y32, and y34, they are all the 3 branches that are connected to bus 3. And remember that bus number 4 has only one branch connected to it, which is branch y43. So these unique terms, okay, they are what we call the self-emittance term, yeah, the self-emittance term. So self-emittance is defined as the summation of all the emittance that are connected to the bus. So if you look at bus 1, the summations of all the emittance that are connected to bus 1 are this. If you look at bus 2, the summations of all the emittance that are connected to bus 2 is this. If you look at bus 4, the summations of all the emittance that are connected to bus 4 is only this single term. So we define this as the self-emittance as this: y11 for bus 1, y22 for bus 2, y33, and y44. And the remaining terms that we have not defined, such as this one, this one, and this one, we call them the off-diagonal element. And just now we mentioned that whether you mention them as y12 or y21, it doesn't matter. They are referring to the same branch, and therefore they have the same value. So if we say that y12, we take the entirety of it, including the sign, and negative y12 is equals to y12, and negative y21 is equals to y21, then we can say that y12 and y21, they are the same, because these two terms are the same. Okay, and another example, we know that a negative y13 is the same as negative y31, and we define negative y13 as y13, and we define negative y31 as y31, and if these two are the same, then these two are the same. Okay, and the reason that we include the negative value, the negative sign, yeah, in all our definitions of this capital letter Y is so that we can write this term into a more uniform manner, such as this, so that we can avoid writing uh, subtractions or summations in certain terms. Instead, we can write all terms, okay, as summation for uniformity. So notice this self-admittance term Y11, Y22, Y33, and Y44 that we had defined earlier here. They are located, okay, if you notice, in the diagonal position of this equation. And the remaining one that is not on the diagonal position, we simply call them the off-diagonal elements. And if you can notice a trend over here, all these off-diagonal elements, they are the reflections of each other. Okay, take for example, Y21 is a reflection of Y12 on the diagonal line over here. Okay, Y12 reflect to Y21 on the diagonal line. Y13 and Y31 and Y13, they are the reflections of each other over the diagonal line. Y23 and Y32, they are reflections of each other over the diagonal line as well. Okay, so this is what we call the off-diagonal element, and the reflections of each of these off-diagonal elements, they have the same value with each other. So with this compact and uniform manner of writing our KCL of our 4-bus network, we can go ahead and represent them in matrix form, such as this. The reason that we want to convert them into matrix form is so that we can handle them more easily, and matrix is also a very efficient way to handle large numbers of parallel equations. In this case, a 4-bus network with 4 equations, they are still quite manageable. But imagine when the network becomes larger later on, and we have even more numbers of parallel equations, matrix will be very useful. So converting them into matrix is simply rearranging by factoring out, yeah, all the voltage onto one side, and the terms of all the voltage into another matrix like this, and the current into another matrix like this. So this is also a good opportunity for you to stop if you have forgotten how to handle multiplications of matrix. And a slight recall for people who have forgotten is to handle the multiplications of matrix, you simply take row number 1, multiply this entire column to get the first equation. The second row of this column, multiply this entire vector to get these equations, and so on and so forth. So we can rewrite this big matrix into something more compact, okay, like this. We simply represent this matrix I as a bold letter I, this matrix Y as bold letter Y, and this matrix V as a bold letter V. So we can see that the initial definition that I is equals to YV eventually comes back into bold letter I equals to YV. So the way we calculate currents, from this basic I equals to YV equation, initially, we derive the slightly more complicated parallel equations, which we convert into matrix and come back to this form. So we can see that it goes into one full circle. Of course, when we write this one, we have to remember what we have defined for our Y value. which is the self-admittance given to you here. Okay, YII. Okay, YII being I can be any value between bus 1 to bus 4. It can be Y11, Y22, Y33, or Y44. And it will be the summations, okay, between of all the branch that is connecting today for the bus. And we also have the off-diagonal element that we mentioned and defined earlier. Y12 equals to Y21, or in generic term, Yij equals to Yj1. Well, so this is the end of the part 1 for power flow analysis. So part 1 of power flow analysis simply recall back and refresh how we analyze KCL, how we handle metrics, and how we derived the parallel equations for a 4-bus network. And in part 2, we will see how are we going to apply this same concept onto a more generic network, and then we are ready to derive our power flow equations. Right. Thank you for tuning in and looking forward to see you in part 2 of power flow analysis. Thank you.